Okay, so this is just to sort of say where we've gone with this. So d equals 1 is percolation, right? Just to remind you about that. Randomly adding trees. And so here's some extra pieces. Below this critical density, no fires take off. This was about 0.57 in this case. Or, very small ones, right? There's some like logarithmic thing there. And above it, you've got a percolating cluster of trees. You're in bad shape. It's, you've got a chance that it will, be hit every time. It's built independent of that underlying distribution, right? So the fact that the lightning is more up in this corner, this system has no idea about that. But has a good chance, certainly as it gets further above this critical threshold, of creating a cluster that connects into that corner or gets close to that corner is a lot of trouble. So there's really so here's the big piece here, and you have this in your assignments now. So theoretically, only at that threshold is when you have a power law size distribution of forest fires. So it's really truncated below the threshold. And as you get to the threshold, it starts to kind of move out and out and out until you get a power law. And then what you start to get on the other side is lots of small forest fires again, but then just this big spike of a huge one. Because there's this big giant component and all these little ones, right? So you can have all these little forest fires or a monstrous one. So as you move through that threshold, there's only that one point where you get this power law size distribution. Randomness, featureless. Forests are random and featureless. Hot, on the other hand, power law distribution, it doesn't really matter, right? There's a lot of variability. You can have different densities below, certainly away from the percolation threshold. And for this kind of system, for a square grid system, there's no specialness of a critical threshold. So it's moved away. It's lifted that problem away because that was weird. Most of the states are okay, and it's not bad if the uncertainty is well characterized. It's still, you could have these giant things explode, right? That's really bad. But if it's well characterized, it's kind of okay. We can handle some of this uncertainty. But if this is characterized poorly or it changes, right? The environment changes, then failures become, and you don't adapt, then you get into more and more trouble. So that's an extra level of like how fast you can adapt these things.